If we're going to talk about mechanisms of inhaled anesthetic action, it implies something. It implies that we know what anesthesia is. Now, you're all anesthetists. Do you know what anesthesia is? Tell me, what is anesthesia? You do it every day. Do you know what it is? What is the anesthetic state? How would you define it? Give me a definition.
The patient can't remember and the patient doesn't move.
That's the definition. There you got it. That's the whole thing. But someone would say to you, well, yeah, but what about unconsciousness? What would you say to that person?
If he can't remember, it doesn't matter whether he's conscious or not.
It's irrelevant, isn't it? And someone else would say to you, but what about analgesia?
Still can't remember.
So you can't remember. And how would you define analgesia?
Pain-free state?
Pain-free. How would you know someone is pain-free?
They would have to tell us.
They'd have to tell
In
us.
some way, whether it's through autonomic reflexes or verbally.
And if you have a patient and you have a surgical incision, what does that tell you with the inhaled anesthetics? What happens to the autonomic responses?
You should, if the patient doesn't have any analgesia and your heart rate goes up or your blood pressure goes up, you can believe that the patient is in pain.
Well, they're having some element of pain, aren't they?
Mm-hmm.
We hope that it's not very great.
Yeah.
Is that what you see?
Well, I try to prevent that, so no, not too
How
often.
do you prevent it?
By giving opioids.
So you have to give opioids. You can't depend on the inhaled anesthetics by themselves, can you?
No.
So they're not very good analgesic agents.
Correct.
Okay. Well, someone would say to you, the definition of anesthesia must include muscle relaxation. Would you agree with that?
Well, the inhaled anesthetics themselves provide some muscle relaxation. As long as the patient's not moving, the surgeon can do the operation. And some operations, we don't use muscle relaxants at all.
So maybe relaxation is an important part of the definition of anesthesia.
Correct.
Okay. But maybe it isn't. And that's what I'm going to tell you in just a minute. Let's go through those answers again. I'm in complete agreement with your definition of anesthesia. Anesthesia, for an inhaled anesthetic, is a reversible state. We didn't say that, but we all assumed that, didn't we? That's mediated by the central nervous system. That state is one that produces immobility in the face of noxious stimuli and amnesia, that is unawareness. And that's it. That's everything. Everything else is irrelevant. Everything else is a side effect. The immobility that's produced by anesthetics was recognized by the first great anesthetist, who was John Snow, giving ether anesthesia, saying that ether contributes benefits. Besides preventing pain, it keeps patients still, who otherwise would not be. That must be the first discoverer of MAC, isn't it? And amnesia, the inability to remember events during anesthesia, is what almost all patients want. They don't want to know what's going on. And it's produced by all inhaled anesthetics. Every last one of them produces amnesia. But unconsciousness is irrelevant. Because as you say, if you can't remember and you can't move, how would you ever know? It's probably there. Probably our patients are unconscious. But it doesn't matter. It can't be measured. And suppression of reflexes and analgesia are similarly irrelevant and probably don't exist. We know that from the sort of thing that we talked about, that a patient who is anesthetized and who receives a surgical incision will respond to that, and we'll see that in a bit in some of the movie scenes from the operating room. The blood pressure goes up and the pulse rate goes up. We know that the inhaled anesthetics do not produce complete analgesia. We know that surgical stimulation increases ventilation. From a study that Jim France and I did many years ago, we measured ventilation before surgery at 1 Mac, at 1.5 Mac, and at 2 Mac, and then the surgeon made an incision, and we measured ventilation during surgery, and it increased at every anesthetic concentration. That doesn't bespeak suppression of autonomic reflexes. That says the patient's feeling something, but the patient's not moving, and the patient didn't remember. And relaxation is irrelevant. We know that the potent inhaled anesthetics cause profound relaxation. We're going to see some illustrations of that are really great. But nitrous oxide does not. Go into a pressure chamber with a volunteer, as I've done, and give them 1.5 atmospheres of nitrous oxide. And what have you got? You've got a volunteer who is apostopnic. The head's on the table and the heels are on the table, but nothing in between is on the table. He's rigid as a board. And to get an endotracheal tube in requires that you give a muscle relaxant. Well, you can pry the jaws apart and you get the endotracheal tube in, but that's not really a very smooth approach. Now, is there a simple explanation that explains all of inhaled anesthesia? Yes, there is. And this was given to me by Neil Harrison. This is the complete explanation for how inhaled anesthetics work. You can see that it involves a membrane, a miracle, and then anesthesia. But the bigger miracle is when the anesthetic leaves the membrane and recovery occurs. And that, of course, is the end. Nah, couldn't be the end. We have to talk a little bit about mechanisms of anesthesia. Now, regarding immobility, we've learned where anesthetics act. Where do they act? The spinal cord. Okay, so if we're going to study this, we have to study effects of inhaled anesthetics on the spinal cord. We'll keep that in the back of our mind. And now we'll go back more than 100 years to two fellows named Meyer and Overton. What did they say? What was the Meyer-Overton hypothesis? We got an answer right back here.
That anesthetic potency was related to its lipophilicity.
Exactly so. And when you say related, you mean directly related.
Directly related, yeah.
So if you have something that's more lipophilic, it will be more potent.
Correct.
And less lipophilic, less potent. And there's, in fact, an equation that describes this. So if you take some index of potency, like MAC, and multiply it by some index of lipophilicity, you get a constant. You get a constant. In rats, the constant equals approximately 1.8 atmospheres. And we can see that in this slide, which shows the MAC and the oil gas partition coefficient for 6 different anesthetics, which vary widely in their MAC. So nitrous oxide MAC is 1.8 atmospheres, and methoxyfluorine's MAC is 0.002 atmospheres. What is it? That's a 1,000-fold range of MAC values. Here's the corresponding lipid values. And if you take these two and multiply them together, note how invariant that constant is. One of the really astounding relationships in science. We can do that or display that graphically, as I've done here. You increase the oil gas partition coefficient, you decrease MAC. And the correlation coefficient on that is 0.99 something. There's an absence of an effect of affinity to water. So this is affinity to oil, but affinity to water doesn't change things, at least so it seems. So you look at the Meyer-Overton constant. Remember, that's the MAC times the lipophilicity equals 1.8 atmospheres. It doesn't change when we change the saline gas partition coefficient, when we change the affinity to water. At least for conventional anesthetics, it doesn't change. So what does this imply? If anesthetic potency is correlated with lipophilicity, where are the anesthetics acting? They're in the cord, but where in the cord? Where in the cord?
I think it just means on a very basic level they're acting at the membrane bilayer.
Yes,
of
and
nerves.
where at the membrane bilayer?
The lipophilic sites of the membrane bilayer. I mean,
So-
there's hydrophobic sites and hydrophilic sites.
Right.
I think it means that these anesthetics will wedge in these sites and cause disruption of the normal neuronal transmission mechanism
By some method that we don't know.
by some method that we don't know.
So here's the bilayer. There are the head groups, and here's the lipid, long chain extending down. And we got water out here and water out here. And tell me where I should go with my finger where the anesthetic is acting.
Between,
Right in between, yeah, somewhere in here, huh? That's where Meyer and Overton say the anesthetics are acting. Now there's a problem with that. The problem is that not all anesthetics follow the Meyer-Overton constant. We've got anesthetics like alcohols that are more potent than their lipophilicity predicts. And we have some very special compounds called transitional compounds that are less potent than their lipophilicity predicts. And then we have compounds like non-immobilizers. Everybody know what a non-immobilizer is? What does its name imply? Well, if it's a non-immobilizer, what doesn't it do? Doesn't create immobility. I mean, here's a non-immobilizer. That's a hexane, and it's a non-immobilizer. Here's an anesthetic. Same thing, except that two of the CF2 groups are missing. And that's an anesthetic, very nice anesthetic, in fact. Didn't cause arrhythmias, it would be even nicer. Non-immobilizer, an anesthetic. Creates immobility. Doesn't create immobility by itself or in combination with anesthetics. So you add this to a desflurane anesthetic or an isoflurane anesthetic, and it doesn't decrease the amount of isoflurane or desflurane that's required for anesthesia, no matter how much you give. So that doesn't fit with the Meyer-Overton hypothesis. It has a reasonable lipophilicity, and you would predict that it should be anesthetic, but it isn't. It isn't anesthetic. And what distinguishes these compounds is their affinity to water. Remember, we showed you that affinity to water for conventional anesthetics had nothing to do with their potency. But when you look at a broader range, we were looking only at a tenfold range. This is, let's see, how many orders of magnitude? 1, 2, 3, 4, 5, 6, 7 orders of magnitude. Now you see that there is an effect of affinity to water. And the greater the affinity, the lower the Meyer-Overton constant. Remember, this was 1.8 atmospheres? Down here, it's maybe a tenth of an atmosphere. And for the transitional compounds, it goes well above 1.8 atmospheres. So we've got to add something else to our definition of anesthesia and what that implies. Now, you gave us a suggestion that the Meyer-Overton hypothesis and the correlation with lipophilicity implied that anesthetics were working here in the center of the membrane. What does this additional information tell you about where anesthetics are working?
They're actually working inside of the cell itself.
They're working in the cell, but where at the membrane?
Well,
Might
they could be working more at the heads of the molecules, are saying.
Exactly. So they've got to have one foot in water and the other foot in the lipid. They've got to work at an interface. It might be here. It might be at a protein interface with water, where within the protein it might be hydrophobic, and outside it might be something that has an affinity to water. So it has to have both a polar and a nonpolar component to it, wherever it's working. It has to be amphipathic. We say it probably acts at an interface, but which one? Perhaps it acts at one of these. There could be an aqueous pocket within a protein. We didn't mention that. And it could be an ion channel. Ion channels are ionophores, holes through membranes. And there are a lot of potential targets that we might consider. Some of these might be excitatory ionophores, or others might be inhibitory ionophores. How would you explain anesthesia by an action on an inhibitory ionophore?
Acting on certain receptors like glycine or GABA.
So those would be the specific receptors where you might get enhancement, as this slide suggests, or you might get depression of excitatory ionophores. And there's a list of ionophores that have been shown to be influenced by anesthetics in ways that could explain anesthesia. All of these all of these are plausible mediators of anesthesia. Does plausible mean relevant? No. I got one person shaking his head. Does anyone else want to shake their head? You all want to shake your heads. Let's see a raise of hands. How many want to shake your heads? Plausible does not mean necessarily relevant, although there are many people who would say yes, it does. If it works on a receptor, surely that must contribute to some of the anesthetic effect. That's not true, as I'm going to show you in just a moment. Which ones are important, and how do we determine which ones are important? Well, let's look at one example that shows that plausibility does not equal relevancy. Here's the effect of anesthesia on the current produced by acetylcholine application to neuronal acetylcholine receptors. You can see that the concentrations are well within the anesthetic range. In fact, show a great sensitivity of the acetylcholine receptor. We get blockade of the acetylcholine receptor right about at MAC with sevoflurane, with halothane, and with isoflurane, and the curves overlie each other. It looks great. That's a plausible target. That could be how anesthesia works. Except that when you give drugs that block the acetylcholine receptors, and we're talking about enormous doses of these drugs, we're talking about how much atropine would you give as premedication to a human? How much? Come on now. How much would you give, Jennifer?
0.4 milligrams.
0.4 milligrams to 70 kilograms. Give 10 milligrams per kilogram to a rat. Doesn't change MAC. That's the MAC with the atropine. That's the MAC without the atropine. Give scopolamine 2 milligrams. Or raise that to 10. Or raise it to 100. And you get no effect on anesthetic requirement. 100 milligrams per kilogram of scopolamine produces no change in anesthetic requirement. Or give mecamylamine, which is a blocker of neuronal nicotinic receptors, as opposed to these which block muscarinic receptors. And again, you see no change. Or combine mecamylamine with atropine, and again, you see no change. So plausible does not mean relevant. There are several other receptors that we could talk about. Thus far, what I want to leave with you is the thought that as far as MAC is concerned, the two receptors that may have some relevance are the glycine receptor and the glutamate receptors, particularly NMDA receptors. And thus far, there is scant evidence that the other receptors may be important to the creation of immobility. They may be important to other anesthetic effects, like amnesia. But there isn't evidence, despite the effect on the isolated receptor, that they're important to anesthesia. I'd like to talk a little bit about what's called the 5-carbon hypothesis. And to do that, we need to talk a little bit about some experiments that were done. And the experiments involved compounds like these compounds here. This is an anesthetic, that's a butane, and this is a non-anesthetic, a non-immobilizer, a hexane. You also have to know that the CF2 group from other studies has no anesthetic effect by itself. None. None. So if you give a compound like that should be a 3, that doesn't produce anesthesia. And if you interpose a CF2 in here and interpose any number you like, you also don't get anesthesia. Never get anesthesia with that compound. So the CF2 doesn't add anything. And the experiment that was done that suggests the 5-carbon hypothesis, that was the publication. And here's the experiment. In the experiment, we took compounds that had a hydrogen on either end and added CF2 groups in between. And as you do, you increase the potency of the compound. So this is the alkane's MAC, up to 4 carbons. But then when you go past 4 carbons, you find that potency is lost. Same thing is true with alcohols. again with the CF2 groups in between, the hydrogen on one end and the alcohol group on the other end. Get up to 5 carbons, it increases in potency, but you go beyond that and you lose the potency. These two ends of the molecule are the anesthetizing components of the molecule. And as you separate them more and more, you increase the potency to a maximum at 4 or 5 carbons. And we suggest that the site of action for immobility is in fact 2 sites of action, or has 2 sites within it that are separated by about 5 carbons, which happens also to equal about 5 angstroms. So we have some conclusions regarding immobility. The inhaled anesthetics act on the spinal cord. That's where they produce the immobility. We believe that some modification of the Meyer-Overton hypothesis might explain immobilization, but it has to take into account that potency is not only a function of lipophilicity, it's also a function of hydrophilicity. That the anesthetics are in fact amphipathic and must be in order to cause anesthesia. We conclude that various receptors form plausible targets, but only 1 or 2 of these are likely to be relevant. They don't include the GABA-A receptor, they don't include acetylcholine receptors or serotonin receptors. There are, and we haven't gone into this, specific sites within receptors that have been suggested as targets. The 270th amino acid, for example, in GABA receptors, or glycine receptors, excuse me, has been suggested as a specific anesthetic target. And perhaps, in fact, there are 2 targets, or 2 sites, that are 5 angstroms apart, that are important to the action of inhaled anesthetics. Now, one of the problems is that this says nothing about the other aspect of anesthesia, which is what?
Amnesia.
Amnesia. How do we know that it just isn't the same site? How do you know? How do you know?
The amnesia site is probably in the brain, not in the spinal cord.
Exactly. Exactly. So there must be another mechanism, at least another gross atomic site, an anatomic site. How else do we know that amnesia is not mediated by the same, probably not by the same receptors that mediate MAC?
We can go back to the non-immobilizers. The
Yes.
non-immobilizers do produce amnesia, but they do not produce immobility.
Exactly so. So how do you know that an animal or a human is amnestic? Well, you do the Toyota test. What's the Toyota test? You take an animal, a rat, and put the animal in a chamber in which there's a grid which can be electrified. And you present the animal with a light at the top of the chamber and then a shock. So the light goes on for 30 seconds, and at the end of the 30-second period, the animal gets a shock, which the animal doesn't like. And the animal learns to associate the light with a shock. Now, the next day, you bring the animal back into the room, put him in the chamber, and turn the light on. But instead of presenting the animal with a shock, you present the animal with a tone. If the animal has learned to associate the light and the shock, when you present the animal with a tone, the animal will jump. And you can measure the force of jumping. That's why it's called the Toyota test. How high are you going to jump? So you can measure the acceleration that the rat imparts to the whole chamber. You have a little accelerometer in the bottom of the chamber. Now you can do this with the animal breathing an anesthetic, or the animal breathing oxygen, or the animal breathing a non-immobilizer. And the effects are the same. And here are the effects. So the acceleration imparted to the chamber in arbitrary units at a 110 decibel tone. This much with a control animal. So during the training session, the animal has received no anesthetic, no non-immobilizer. But if you give, either as a MAC or a predicted MAC based on lipophilicity, a perfluoropentane, which is a non-immobilizer, or 1,2-dichloropurfluorocyclobutane, you see that you have suppressed this jumping. And you've suppressed it over the concentration range that is the same as the suppression that you see with desferrine or with isoflurane. So where does that say that amnesia is produced as far as the membrane is concerned? What does it say? Where is amnesia produced? Is it at the surface of the membrane or deep within the membrane?
It says amnesia is produced, in the brain site other
Yeah,
than
yeah.
the surface of the membrane.
Would it be surface? Because that implies
That implies
hydrophilicity.
hydrophilicity.
Are the non-immobilizers compounds that have a significant hydrophilicity?
No,
No, they're not. And therefore, where are they acting?
they're acting in the lipophilic portion of the membrane.
Right, so they're acting down in here, or in a protein, but not at the surface of the protein. I'd like to leave you with one thought regarding amnesia, and that is its relationship to anesthesia as defined by Mack. For all of the compounds that we deal with in anesthesia, amnesia is achieved when immobility is achieved. So if you have achieved immobility, you've achieved amnesia. And clinically, that's very important. If you have the anesthetic state that includes immobility, you will have also achieved the other component, which includes amnesia.